Hello, everybody, and welcome to another online seminar presented by Head Acoustics. My name is Jacob, and I will be your host today. Today's topic will center on headphone testing and specifically dive into something that we're calling MDAQS, Multidimensional Audio Quality Score. This is a new, novel, and much needed method for measuring audio quality in an audio system, and we will take a look at headphones in particular. As we've done in the past, we got together with the awesome team at headphone.org to take some of the very best headphones and put them through their paces. We wanted to test them and see how their performance stacked up in terms of a traditional performance indicator, like frequency response, and the new MDAQS metric. So first up, a few words just to set the foundation for everything we'll be discussing today. Since we're testing headphones and their audio playback capabilities, we want to grab the latest and greatest head and torso simulator. So we're using the Super HMS, what we call the HMS 2.3 LNHEC, which uses low noise ears and anatomically shaped ears and ear canals, compliant with ITU-T P57 4.4. And we want to place our equipment in a quiet space to remove all unwanted background noises and disturbances. We previously presented a whole seminar on the Super HMS in very great detail. So for the purpose of this session, we're just wanting to emphasize three things. Number one, the low noise ear simulators are used and chosen here specifically because we want to accurately capture every single note and artifact in the headphone playback. Number two, the anatomically shaped ears, concha, and ear canals, we use those because we want to get the most accurate headphone placement, especially for in-ear devices. And number three, the large circular base that the pinna is mounted on, that's very helpful because it ensures that we get a nice even seal and fit for the larger circumaural, sometimes known as over-ear or over-the-ear headphones. So that being said, quickly referring to the slide you can see in the top left, we're using a PC with our Aqua software on there. Aqua is the signal generation and analysis tool that we have. And that is, of course, equipped with the MDAQS algorithm to perform the audio quality score calculations. In between the Aqua PC and the Super HMS inside our chamber, you'll find the lab core. In very simple terms, the lab core is our data acquisition front end, which acts as an A to D, D to A converter. It relays the stimuli to the headphones under test, either via analog, Bluetooth, what have you. And then, while providing signal conditioning to the ears, it will transmit the recorded binaural signals back to Aqua for analysis. Now, while we made it look fairly simple in that block diagram, placing headphones and earphones on a head and torso can be quite an arduous task. So there's a few key things here that will help us get the best placement possible. In short, number one, we always start with visual placement. So the goal is always to get as realistic as possible. For circumaural devices, we look for how the headphone cup sits over the ears, obviously making sure the pinna isn't folded up, and that the cups are oriented according to the design of the headphone and how they would typically sit on a human. So we, of course, also check that the headphone band is adjusted so that it rests on top of the head and passes across the top of the head at a realistic location. At this point, we'll fire up Aqua and our online analysis tool with some white noise stimuli for playback, and then we'll transmit that signal to the headphones. So what we're looking for here is specifically the spectral characteristics of the headphone playback, where we keep an eye on two things. One, we of course look at the overall level. We want to make sure that we're driving the headphones at an appropriate level. And we're also looking at, quote unquote, the frequency response. We are looking to see whether that frequency response seems realistic for the device that we're measuring, and if there is a good match between left and right ears. Specifically for Aqua users out there, pro tip is we usually change the line width and we enable the draw mix colors so that we can better see when we have overlap and channel matching when you're looking at left and right ear at the same time. So as we look to fine tune our placement, we generally move one headphone cup at a time to get a sense of how the headphone behaves relative to movements up, down, forward, back, as well as to rotations, either by moving the entire headband forward or backwards on top of the head, or if possible, by rotating the headphone cups individually. And again, the goal here is always to get channel matching between left and right. And I know we're making an assumption here that the headphones themselves are channel matched, but bear with us. And then we're, of course, looking at that overall response to make sure that it is right or correct based on the subjective knowledge of the device. And this, of course, can be a little bit difficult, especially with some of the more highly sophisticated DSP-filled headphones, because we don't always know what type of ANC or gain control or spectral shaping processes are built into the headphone and how they react when they're on the ears. So all that being said, and from what you can see in the video here, this, in our experience, it can take upwards of 5 to 10 minutes easily to get this thing exactly right, but it does make a big difference in the results. So once we have a good fit with an appropriate drive voltage, we can start our testing. So does that make sense? All right, we're all on the same page. We're all clear on what we're doing. Let's get testing. Thanks to the folks at headphone.org, we had access to some really great headphones. And as we progressed through our testing, we obviously wanted to capture their frequency responses. This is the most traditional way of representing a headphone's performance and provide an indication of its audio quality. Question: why do we use frequency response? Well, in short, a frequency response plot is something that we sort of all understand. It's what gets posted and shared online, and there's been a fair amount of research that indicates that a frequency response is the key performance indicator. So let's dive in and take a look at our example headphones. As mentioned, we had a really good mix of over-ear and in-ear products. And keep in mind that these were all relatively high-end products. Headphone.org doesn't mess around. So as we examine the graph, first thing to note is that all responses shown here and elsewhere are going to be unequalized, or raw measurements. That means there's no compensation curve applied. Also, it's clear that there's a difference between each of these headphones. We've normalized these to 1K, which allows us to more easily compare the headphones. Some clearly have more bass and others have more treble. But it can be overwhelming to take in. How much data is too much data? Let's split this grouping into over-ear products and in-ear products, respectively. See, now we get a slightly better sense of how each product category generally performs. The over-ear products on the left-hand side are going to have less variation in frequency response. They all sort of follow the same pattern and recipe, and yet they certainly sound different and, to an extent, very unique when we listen to them. So it's curious how that works, eh? On the right-hand side, you'll see the in-ears, and there's a lot more variability there, both in terms of the bass response that they aim for and in the uniformity of the treble reproduction. Perhaps this is better shown by sharing the average response for each product category. Once again, just to be clear, we've normalized the results at 1K just to make things a little simpler, and we can see that the in-ears, shown in blue, on average exhibit about 5 dB higher bass response than the over-ears, shown in magenta, and likewise, there's a decent amount more treble present in the in-ears. This generally agrees very well with best practices regarding tuning from a spectral perspective. And that's all pretty cool, but what does it really mean? And how do we extract meaning from this? Does this really help us judge the perceived quality of the headphones? And how can we easily find which headphone is the most pleasing or the most preferred? So with all those frequency response plots in mind, can we confidently say that one product is better than another? To what degree of confidence? And what about the elements of sound reproduction that is not included in a frequency response? As audio engineers and designers, how do we know we're going in the right direction? What's good and what's bad? And how do our changes affect the performance or the perception of the performance? Obviously, we should listen to the product. However, for various reasons, that might not always be possible or feasible. I think that's exactly where MDAQS comes into play. And my colleague Yanni is here to help us explain.
Thanks, Jacob. Now, why MDAQS? Let's start with a little history lesson. PEAQ, P-E-A-Q, Perceptual Evaluation of Audio Quality, has been around since roughly 1998, but was designed to look at the audio quality relative to compression strategies and encoding methods. Back at that time, it was already known that traditional audio measurements like frequency response were based on sine sweeps, signal to noise, total harmonic distortion, and they were found to not necessarily correlate well with audio codec quality. And a psychoacoustic model had to be used to predict how information is masked by louder audio content adjacent in frequency and time. However, PEAQ was still limited in scope and not designed for, hence not suitable for, acoustic evaluations. It was really only for single-channel digital audio streams after codecs had been applied. And since the days of PEAQ, there really hasn't been any available, accepted, successful, or standardized metric to address the issue of rating the audio quality of an audio system. The alternative, of course, is to engage in subjective listening tests. However, they are time-consuming, expensive, and impractical for everyday use. It's clearly beneficial to substitute listening tests with objective, computer-based methods. Hence, a need for something new that evaluates audio quality as perceived by the user, acoustically and binaurally. MDAQS is a MOS score. A MOS, mean opinion score metric, is a way of assessing the performance of the device under test, and the roots of which are in the subjective jury studies. Jury studies involve asking people to participate in very controlled listening sessions and to rate, either in absolution or comparatively, many different audio samples. The goal being to collect many samples from a broad variety of people, ideally greater than 10,000. The idea with a MOS metric is to have a mathematical model that replaces this large subjective study. However, the final metric can only ever be as strong as the original jury study, so it's imperative that data collection is done with great care, covers all of our use cases, and obtains as many samples as possible. The more training and validation data we can provide the metric, the stronger and more accurate it gets. The benefit of a MOS metric is that every time you want to test a device, an algorithm, a firmware build, or a transducer selection, the metric takes the place of more than 10,000 individual subjective ratings without the logistics, time, and cost of organizing a jury study. MOS metrics today generally include several pre-processing steps, hearing model analysis, and machine learning blocks in order to rate the audio sample in a similar way to the average jury study participants. MDAQS is no different in that regard. However, there are many details that make it unique. In the underlying research for MDAQS, we faced many challenges. Curiously, the first challenge was a very fundamental issue regarding how we can conduct the assessment. We quickly found that absolute category rating doesn't work well for this. Most products are of a sufficient quality that our overall scale gets very compressed. Imagine that instead of operating on a 1 to 5 scale, all results end up between 2.5 and say 3.5, which makes the data inherently noisy and hard to extract value and information from. Instead, we looked at comparison category rating as the main approach. Here, users are presented with 2 audio samples and asked to compare them on a few different parameters with a preference rating of -3 to +3. This approach is also an easy way to verify the data is appropriate, since we can easily check for circular triads, where users rate A is better than B, then B is better than C, then somehow come back to say C is better than A. Then we had to figure out which parameters were appropriate for quantifying the performance of a music playback system in a hearing adequate manner. What is important for human listeners? What is important to your quality perceptions? So we settled on three main subcomponents of MDAQS. MOS-T for timbre represents the spectral properties of the transmission system and the temporal resolution. MOS-D, distortion, represents nonlinearities and the additive noise. MOS-I, the immersion, represents source width, source position, and stereo width. And all calculated together to give us MOS-O, the overall quality representing the overall quality impression. Lastly, we had to choose our source material. So we settled on 6 music signals, which were the same 6 that we used in the subjective jury studies. And while we were at it, we added 2 sweeps for the left side and the right side. Now, MDAQS can be used in a plethora of use cases, from consumer headset and headphones, like in this discussion, car audio systems, stay tuned for the next session, and loudspeakers and smart speakers. Let's dive into the rough overview of the MDAQS algorithm. So the first block highlighted here is the pre-processing block, which is fed by music, which are the 6 listening tests that we used in the jury study, and 2 sine sweeps from 20 Hz to 20 kHz. The pre-processing block contains basic information like sampling rate, alignment, level adjustments, and sets the foundation for the remainder of the algorithm. Each of the subsequent blocks require a lot more processing that is unique to each parameter, although there is, of course, some overlap. The key point here is that there is no single analysis that will fully capture what a human will perceive. Let's start with a look at the analyses for the different attributes. Each block actually contains 5 different analyses, with 1, the delta to a target frequency response curve, being shared by all blocks. This target curve was derived from our listening data and reflects the preference of our subjective participants, obviously in relation to timbre. For distortion, identify which portions are important, and for immersiveness, spatial perception is frequency dependent. We also have spectral flux, used in timbre and immersiveness, indicates how the temporal structure of the signal is reproduced through the system. Also, traditional distortion analyses, like harmonic, linear, and nonlinear components and signal modulation. But specific for immersiveness is the use of a binaural hearing model, which quantifies the spatial perception of human listeners. Now, let's kick it back to Jacob.
Thanks, Yanni. So the question that we really want to try and answer and dive into is, how do we properly design and evaluate headphones? This question is a lot more relevant now because headphones are just getting so much smarter and more sophisticated, and it's time consuming and it's certainly not always feasible to rely on subjective evaluations. As a developer, you're looking for ways to speed up the design process that takes you down the right path of ensuring a good sounding headphone. As a consumer, you're probably looking for something to help you gauge the overall audio quality of the headphone, rather than relying on interpretations of a frequency response measurement and aggregating dozens or hundreds of reviews online. As Floyd Toole wrote back in 2009, I quote, "Frequency response is the single most important aspect of the performance of any audio device. If it is wrong, nothing else matters," end quote. There is a lot of truth to that statement, but is it sufficient? We sit here and grapple with questions like, what about the temporal aspect, phase and group delay? What about imaging and staging? And what about unwanted content like added distortions and noise? What we'd like to share now are a few headphones measured on our Super HMS, where we present the MDAQS results and compare them with their respective frequency responses. This is that next step and more advanced analysis that helps us score and rate those elements of the audio playback that can otherwise be very hard to characterize and quantify. While we can all measure a device frequency response, the additional elements of what constitutes high audio quality can be hard to set up in traditional measurement systems. There are a lot of temporal features in high quality audio where we simply don't have good measurements. We can try with some level versus time analysis, apply psychoacoustic metrics, but the question is still how to draw meaning from those. Instead, as we mentioned, MDAQS is an algorithm forged on thousands of samples and is akin to conducting your own jury study every time you run the calculation. Let's take a look at how MDAQS would rate some of our chosen headphones. So here is a collection of all the headphones we tested. If we recall and sort of adhere to that mantra that frequency response is the single most important aspect of any audio device, and if it's wrong, nothing else matters, then let's try to rank order our headphones according to MOS-T. That's the timbre parameter, the one that represents the spectral and temporal properties of the headphones. However, as we touched on briefly, one of the key ingredients to MOS-T is the delta relative to a target frequency response curve, and therefore it's arguably somewhat akin to looking at frequency response. And if we choose to sort those headphones according to MOS-T, we might get an overall ranking system similar to what we might have achieved by looking at frequency response plots, or perhaps rather a delta frequency response plot where we calculate the average distance to the target curve at multiple frequency points. Either way, we should get a ranking that looks a little bit like the above. You can see that our devices are both in-ear devices and over-ear devices, and there's a few of each kind. The over-ear device happened to be an ANC-capable headphone, and we measure both with ANC on and ANC off. Now remember, all of our MOS dimensions here go on a scale of 1 to 5, and you can see our two in-ears, in-ear 3 and in-ear 5, they rank at the very top along with over-ear product number 4 and in-ear product number 6 with very, very excellent MOS-T or timbre scores. As a result, we ranked them according to that ranking scale on the far right from 1 all the way down to 13. Now, if we decide to factor in the other components, such as distortions and additive noise accounted for in MOS-D, and the source width and position, the immersion that's accounted for in MOS-I, you can see that poor devices, they remain poor. So, 10 through 13 of the previous ranking, they really don't change. However, there's a bit of a shuffle in that top 9. And this is important for two reasons. It means that the premise that frequency response matters, essentially that, what dominates is the MOS-T or the timbre, is indeed true. A good device is a good device if you measure the frequency response. There's no bones about it. All of our top 9 devices score greater than 4.4 in the MOS-T dimension. However, and this is that second point, it also means that there is more to the overall audio quality perception that could possibly be captured in a frequency response. And MDAQS allows us to quantify those parameters. By the way, as a point of curiosity, all our headphones here do score really well. And we have 2 in-ear devices at the top. I'm not sure I would have guessed that before we got started. But anyway, let's jump into a comparison to highlight how and why MDAQS can maybe help us. So here we're showing 2 very nice in-ear devices. They both have good channel matching. However, the frequency response tells us that there are differences. We can see them, we can hear them. The difference generally is somewhere around 5 dB in the upper bass/lower mid region, and maybe a few dB in the mid treble range, right around 4 to 5K. But which one sounds better? Can you tell from that frequency response plot? If you were tuning the blue device, let's say, what changes would you make and why? Or vice versa. Now, let's see what the MDAQS algorithm gives us. Across the board, these 2 devices actually score remarkably similar. There's 1/10 of a MOS point difference between them in the 3 sub-MOS categories, which results in an overall quality score of 4.23 for the blue device, that's in-ear 1, and 4.21 for in-ear number 4. So despite their different frequency responses, they are actually both very comparable and good, for that matter, in terms of the overall audio quality perception for multiple music sources. And as an audio engineer, you can now easily start to track the changes in audio quality perception as you start to fine-tune your product, because not everything is determined by that frequency response. Now let's go to something a little more extreme, comparing the best and the worst in-ear device we had at hand. First, take a glance at that frequency response, and you can see they're nowhere near each other. There's clearly deviation across the board. And if you look a little closer, you can see the channel matching isn't as tight with in-ear 2 shown in gray. But to be fair, we're only talking about a few dB here and there in terms of the channel matchings. So either way, I think everyone is prepared to rate in-ear 6 higher than in-ear 2, right? Here's what MDAQS does for us. Now, obviously, we can see that MOS-T, there's almost a whole MOS point difference here between the two. Clearly, the heavy bass and the peaky mid-treble is being punished a little bit in MDAQS, and I should say, in our subjective jury studies. Even more extreme was MOS-D. There's almost 2 MOS points of separation between the two devices in favor of in-ear 6, which is the magenta one. And when we listen back to the recordings, we can hear that a lot of this additive noise that's being punished with in-ear 2, shown in gray, is really showing up in the form of traditional distortion components and crosstalk. And while MOS-I does favor the gray in-ear 2 device by almost a whole MOS point, there's just no making up for lost ground in the first 2. So you can see the big difference in the overall quality perception, right? The timbre dimension and the distortion and noise dimension, the gap is so big that even though the source width and position is actually fairly well designed and done with in-ear 2, it just doesn't make up for the fact that people are not going to rate it well. On the other hand, though, the magenta in-ear device 6 just scores exceptionally well and is, in fact, the highest overall rated device that we had. Nonetheless, what this does is the gray in-ear 2 device designers highlights a couple of things that could be improved upon to bring up the overall performance. Now, let's take a look at the best and worst over-ear products. In this case, I think this comparison might be a little easier just by looking at the frequency response. The yellow device lacks a little bit of bass, it has a funny notch somewhere around 400 hertz rather than a nice smooth extended dip, and it clearly doesn't measure well in the high treble. Most people would look at these two graphs and immediately point to the cyan device as the better product. Let's see how MDAQS scores these devices. Sure enough, the cyan product scores almost a full MOS point higher in MOS-T, and despite MOS-D and MOS-I actually being fairly close, there's just no catching up due to the large difference in the frequency response, as clearly determined by the MOS-T dimension. So as the designer of the yellow device, there are obvious areas to fix in the spectral domain, and as the designer of the cyan device, there must be small gains to be had in terms of better spatial reproduction, source width, and position that could make this product even better. So, we could spend hours diving into all these results, but we have to watch the time. So, what tentative conclusions can we draw from our MDAQS analysis? Well, in short, MDAQS is a more holistic approach to quality evaluation that relies on more than just a frequency response measurement and yet provides us with a clear indication of performance. We'll mention again that frequency response is the most important indicator of performance, but where frequency responses can be a little difficult to decipher and challenging to use for rank ordering devices, MDAQS gives us easy to interpret numbers and allows us to identify strengths and weaknesses of the devices. So we can with greater confidence claim that in-ear 6 and in-ear 5 are just fantastic devices and were the best in our test. Over-ear 4 was just slightly above average, whereas over-ear 1 was a little bit below average. And finally, in-ear 2 was the worst of our sample headphones. And please keep in mind that we to some extent are picking nits here because our selection of headphones we were working with in conjunction with headfi.org was certainly of a high caliber. So even the worst headphone wasn't exactly a bad headphone. However, it's nonetheless exciting to see MDAQS being able to differentiate and show preferences in the audio playback performance. Either way, we can conclusively state which device is the best and which has the most room for improvement, and crucially, where that improvement is. And you can do this from your lab in North America, Asia, Europe, or wherever you are. And so from an engineering perspective, you can quickly deliver devices to golden ears in your organization that have already been tuned to a fairly high degree and thereby speed up your development cycle. So lastly, what are the take-home messages that we want to leave you with? Well, we went through the basic test setup, we recommended some equipment and provided tips and guidelines for better headphone measurements. We looked at frequency response plots and touched on some of their limitations. We briefly went over MDAQS, and then we took a little bit of a deeper dive into how some very high-end headphones perform. So I have a few questions and answers that I hope we can sort of all agree on here. First one is, how important is frequency response? Very is the answer. Is there more to the quality perception than what can be captured in a frequency response? Yes, we would argue. Does MDAQS include elements beyond frequency response? It certainly does. Does MDAQS offer a more holistic measure of quality perception? Yes. And does MDAQS provide an easy way to interpret good and bad devices? It does. Ultimately, MDAQS is another tool, a powerful tool, we'd argue, in our tool belt for evaluating audio playback devices. This is something that could benefit developers. It could be used to help form standards and benchmarks for test labs that are ranking devices, and could be useful to consumers for evaluating headphone performance, certainly for those that are maybe a little bit scared to take the step and start relying purely on frequency responses. And on that note, we'd like to thank you very much for attending today's session. We will now be opening up the Q&A, where we will welcome your questions and engage in discussions. Thank you.